Okay, so here we're interested in nested expectations. And actually, I should say this course, the material is on my homepage. So this is a course on stochastic simulations, part of a PhD program here, and it's essentially turned into a 16-lecture course on multi-level methods in a whole variety of different contexts. So that might be of interest to some people. So here, what we're interested in are nested expectations. So as it shows here, we have an expected value with respect to a random variable y of a function of an expected value of x conditional on y. Okay, and here, in principle, x and y can be either scalar or multidimensional. What's going to be assumed is that for a given outer sample y, that we can simulate x conditional on y with an order 1 cost. And then this is actually good in response to that last question. Whether this is an easy problem or a difficult problem depends on this function f and how nice the function is. If it's twice differentiable, that's great. If it's something like the max function giving continuous and piecewise twice differentiable, then that's slightly nastier, but that's quite a typical case. And then the one that's really difficult is if there's a discontinuity. So if, for example, f is the Heaviside function, which is 1 if x is positive and 0 if x is negative. Okay. So that's the outline. I'll talk about the motivation for this, and then how do we handle this with multi-level. So the first application of this, I think, in the literature was these colleagues of mine in 2013. And they were looking at a financial modeling problem where they had this model of whether or not a particular firm becomes bankrupt. So this I superscript here is the index of the firm. So there's a sort of drift and volatility term associated with this, but the volatility bit, there are two separate bits. This term with the capital B, dWt, that WT is the same WT for all the different firms. So that's what's called the systemic risk behavior. And then there's this extra bit, which is unique to each individual firm. So this dWi, it's a different Brownian motion for each one of the firms. So this reflects the fact that, if you have a bunch of car companies, then if there's new legislation about electric cars, that affects all of the companies in the car industry. But if one particular car company, I don't know, fires their CEO, that's going to affect their stock, but it won't necessarily affect the stock of the other companies. Okay, so it's systemic risk affects them all. Idiosyncratic risk only affects that particular company. And so in this model, firms are viewed as bankrupt if X drops below 0. And what they were interested in this problem was what happens in the limit as the number of firms tends to infinity. And the quantity Y here is the systemic risk factor. And so what they were interested in was the fraction of the firms which are bankrupt before the end of the simulation time. And so it turns out this quantity F in this context was continuous and piecewise linear. Oops. This led into other things that Al, Haji, and I were interested in, which come out of finance. So value at risk and conditional value at risk. So we did our first paper in 2019. There were previous papers on Monte Carlo simulation. Particularly these two papers are very significant in the literature. The issue with banks and risk calculations is it's kind of a worst case scenario. Suppose that in a particular week, you don't change the exact holdings of stocks, bonds, options, and things that the bank holds. Just how much can the value of your portfolio change in 1 week? And in particular, can it exceed the cash reserves, which is what the bank regulators are concerned about. So in that context, we're interested in the current value of the portfolio of all of these financial instruments that the bank holds. And then the future value of that portfolio is the expected value of the portfolio conditional on what happens for the next week. And so what you're interested in then is what's the loss? What's the difference between the current value of the portfolio minus the value of the portfolio in a week's time contingent on the Brownian motions, that have driven the evolution of all the stock values. So one way of looking at it is what's the probability eta that the loss exceeds some value, but actually VAR, value at risk, is defined the other way around. It specifies eta and works out the corresponding L eta that goes with it. So it's basically saying that what's the size of loss which you will only encounter with a probability of no more than, say, 2%. That's the kind of question that they're asking. Let's not worry about that. But the key thing here is that loss is a conditional expectation. And so a loss probability is a Heaviside function applied to that difference. So this is an example of where we get these nasty discontinuities coming in. Then there's some other work I've also done with other colleagues in a medical application. And this is to do with something called expected value of partial perfect information. And then there's these other bits as well. So in medicine, there are huge uncertainties. There's all kinds of interest in future personalized medicine, which will lead to interesting questions. But let's look at this second question here. If we have some particular medical sort of condition and a number of possible treatments, then if we're not doing personalized medicine, we're looking at saying, okay, if somebody has such and such a disease, we want to select what is the best treatment to use for everybody that has that disease. However, in assessing the benefits of different treatments, there's a lot of uncertainty. There's only a limited amount of knowledge of each of the treatments. They've maybe been tested with a small sample of patients. That necessarily won't be perfectly reflective of the entire population that's being treated. And so the question here is, if we did a more detailed medical study with a larger sample of patients, would that additional information allow us to do a better job of choosing the right treatment to apply to the entire country? And does the cost of that, is the cost of that research justified, therefore, because of the improvements that it will give in the overall treatment? And so that's the question of interest here. So in this context, if we have a cost-effectiveness model for the benefit of a particular treatment, within that model, there are various parameters whose values we don't precisely know. So we view those parameters as being random variables coming from some specified probability distribution. Okay. We've got some finite set of treatments, say 3 different treatments. Now, if we don't precisely know what the values of X and Y are, so they're modeled as being a random variable out of some distribution, then on average, if we average over those different possible values of X and Y, then this quantity here, the expected value of F sub D, is the expected benefit from using treatment D and applying that to the whole population with this disease. And then what we want to do is to choose whichever treatment maximizes that. Okay, so we want to take the maximum over D of the expected value of F of D. On the other hand, if somehow magically we could find what the true value of X and Y is, then we would simply maximize D for that particular value of X and Y. So if we have that perfect information, now remember, we don't yet know what the exact value of X and Y is. All we know is that if we did know them, then we would maximize over D. So what we can say is that on average, if we did the experiments to get the perfect knowledge, then this then would be the outcome on average. And so that difference is what's called the expected value of perfect information. It's how much better on average we would be from conducting this medical experiment to determine the true values of X and Y. Now here, that's fine. We've got expectations. We can do those with Monte Carlo. That's fine. Where it gets interesting is if we can't eliminate all of the uncertainty, and so we can determine y, but we can't determine x. So in that case, what we end up with is this one here. So we get the expected value of partial perfect information. So this is what we got if we had no information. And this is the one that we have if we're able to determine y, but not able to determine x. Okay, so inside here, it says that if we know y, then we take an expectation with respect to x, and then we maximize that over all of the different treatments. But we don't yet know what y is, and so the benefits we anticipate, we have to do an outer average over the y. And so this is why we end up with a nested simulation problem, a nested expectation problem. And one of the other people who was working on this project with us, Takashi Goda from Tokyo, he was interested in it from an oil exploration point of view. So if they're developing a new oil reservoir, they have a question as to whether or not to put down another exploratory well in order to get more information about the reservoir in order to maybe be able to extract more oil from it in the long term. And so, they have to compare the cost of putting down a new exploratory well versus how much information is that going to give us, and what benefits are we going to get from that additional information. It's very much the same kind of question. Then there's also another thing called expected value of sample information. It's just a further complication on all of this. I think I'll skip over that slide. But again, we've got nested expectations. Okay, so that's trying to set up, why I'm interested in this question. So let's come back to this problem in a very sort of generic way. So we want the expected value, that's an expectation with respect to y, the outer variable, of a function of the conditional expectation of x given y. So a standard Monte Carlo estimator for this might use n outer samples for the expectation with respect to y, and then for each one of those y samples, use an average of m inner samples for x. So this x bar here is this average of m samples of x conditional on the value of y. Okay. So then, how should we choose m and n to get an epsilon squared mean squared error, or an epsilon root mean squared error? So if x is scalar, if the function is twice differentiable and has a bounded second derivative, then if we do a Taylor series expansion, we're going to do the expansion around the conditional expected value of x given y. Okay, so we're taking x bar is equal to the expected value plus this delta x. And so doing the Taylor series expansion, we get f plus f prime delta x plus a half f double prime times delta x squared. Now, when we then do take the expected value of that, the expected value of delta x is 0. Okay, because on average, the expected value of x bar is just the expected value of x. So what we have then is the difference between the expected value of f of x bar minus minus f of the expected value of x conditional on y, because that's what we had here, and that's what we expanded around. That difference is less than or equal to k over 2m. K is this bound on f double prime. 2m, m is the number of inner samples, times the variance of x conditional on y. Okay, so that gives a sense of how big the error is from the inner sampling. So that's for a particular y, but then we can average that over the distribution of y values. And so what we end up with is this. And what that says is that the overall bias in our problem scales as 1 over the number of inner samples. And so actually the number of inner samples we want, we need to use if we want epsilon root mean square accuracy overall, scales like epsilon to the -1. We also, as usual for Monte Carlo, need order epsilon to the -2 outer samples. And so the overall cost will scale like epsilon to the -3. Okay. And then the usual multi-level thing is that we want to do better than that. Right. So Gordia and Janja, this is one of the papers I mentioned before, they were looking at this in the context of this Heaviside function, this discontinuous behavior. They actually managed to prove that the inner estimator again has an order m to the -1 variance, and that leads to a bias in the outer estimate of the same order. And so again, you end up with a conclusion that you have epsilon to the -3 work. And then this other paper I mentioned by Brody, Du, and Moalemi, they used adaptive sampling. So if you have a Heaviside function, so it's either 0 or it's 1. Okay. So really the only question you have to answer is, is the expected value of x given y, is it positive or is it negative? Now, if it's very positive, you probably won't need very many samples of x conditional on y in order to be sure that the expected value is positive. And likewise, if the expected value is negative and large, you probably won't need very many samples of x to know that the expected value is negative. It's only if the expected value of x conditional on y is close to 0 that you really need to be careful, and you need a lot of inner samples to be sure whether the average is positive or negative. And so that's what they did, that they had an adaptive sampling algorithm that, based on how far you were from 0, that controlled how many samples it used. Let's not worry about the details, but what they were able to do was to reduce the overall complexity to order epsilon to the -5/2. Okay, so it's better than the epsilon to the -3, but it's not the epsilon to minus 2, which is what we always aim for. Okay, so what do we do with multi-level? Well, it's really rather simple. On level L, we're going to use 2 to the L inner samples to compute the average of X. Now, what do we do on level L minus 1? Well, we can use a completely independent set of 2 to the L minus 1 samples. It's the same Y, but conditional on that Y, we can use a completely different set of X samples conditional on it to compute the course average. So X bar C. If F is globally Lipschitz, then F of the fine average minus F of the coarse average is just going to be proportional to the difference between X fine and X coarse. X fine and X coarse will both differ from the true expected X by an amount that's of order 2 to the minus L over 2. Now that's because the variance of X bar will behave like 1 over the number of samples, ML. So the variance behaves like 2 to the minus L. So the root mean square error or difference behaves like 2 to the minus L over 2. So that's the difference in the outputs. The variance will behave like the square of that. So the variance behaves like 2 to the minus L. The cost is proportional to the number of inner samples. The cost goes like 2 to the L. So in terms of the multi-level theorem, that's a beta of 1, a gamma of 1. And so overall, it's an epsilon to the minus 2 log epsilon squared complexity. Okay, so that's better than what we had before. We can actually do something that's even better than that, that if F is twice differentiable, then again on level L, we're going to use 2 to the L inner samples. But when we couple that to a calculation on level L minus 1, rather than using a completely independent set of samples for level L minus 1, we're going to again use these 2 to the L samples, but we're going to split them into 2 halves, two subsets of size 2 to the L minus 1. And so we average 1/2 to get this estimator, and we average the other half to get the second estimate. And what we then have is this as our multi-level correction for level L. It's the difference between F based on the average of all of the 2 to the L samples minus the average of F based on the first half and F based on the second half. Okay, so if you look at this estimator, the expected value of Z is the expected value of F based on 2 to the L samples minus the expected value of F based on 2 to the L minus 1 samples. Okay, so that estimator has the correct form. But the thing that's nice about doing it this way is that, well, imagine if f of x was linear. In fact, suppose f of x is just x. This x bar fine minus the average of each of the 2 coarse x bars, they all cancel out. And so you just get 0. And then that works also in general. For any linear f of x, then this z estimator is identically 0. And if f is not linear but has a bounded second derivative, then you do a sort of Taylor series expansion of what's going on here. And what you get is that z is of order the difference between the x bars, the course group 1 and course group 2 squared. And that behaves like 2 to the minus L. And so the variance behaves like 2 to the minus 2L, while the cost is still 2 to the L. So now we've got a beta of 2, a gamma of 1, and we have an epsilon to the minus 2 complexity without any of the log bits. If we've got this f that's continuous and piecewise linear, so it's not twice differentiable, you can argue it through, and what you get is sort of an in-between case. We end up with a beta of 3/2, a gamma of 1, and that's still good enough to get epsilon to the minus 2 complexity. And that's actually what my colleagues used for their financial credit model. Yeah, because they had a piecewise linear f in their problem. So then that brings us to the nasty case, where we have the discontinuity. So if each of the course averages has the same sign, then the fine average is the average of the two course averages. So it will also have the same sign. And in that case, z is equal to 0. So the only thing which gets interesting is if these two course averages have opposite signs. And so this is when we're very close to 0. So if the expected value of x conditional on y, if that has a bounded probability density near 0, then each of the course averages will differ from the true average, the true expected value, by an amount of order 2 to the minus L over 2. So it's only if the true value lies within a sort of order 2 to the minus L over 2 neighborhood of the origin, it's only then that we get this possibility of the two course averages being on different sides of 0. And that's the time that we get a z of 1, or order 1. It'll actually be plus or minus a half. So with this probability, we have a z of plus or minus a half. So therefore, the variance will be, well, the expected value of z squared is the probability of being non-zero times the magnitude of the non-zero. So it's basically going to scale like 2 to the minus L over 2. But the cost is still 2 to the L. So if we do this, what that's going to give us is a beta of a half, a gamma of 1, and so the overall complexity, we also have an alpha of 1. This is the bad case in the multi-level theorem. We get epsilon to the minus 5/2 complexity. So we haven't yet done better than the work of, who is it? Brody doing MLMC. Okay, so we've matched them. We haven't beaten them yet. Okay, we can make all of this analysis rigorous. But what we can now do is combine this with the ideas of Brody, Du, and MLMC, and do adaptive sampling on each level of correction. So we have this complicated expression, but let's look at the picture. So here we've got the number of inner samples, ML, as a function of how far away we are from zero. So delta is sort of a non-dimensional distance away from having the conditional expected value being equal to zero. So as we increase our multi-level level, we increase the number of samples. But also, as we're close to zero, we use more samples. And so out here, the number of samples behaves like 2 to the L. Close to zero, the number of samples behaves like 4 to the L. And so that concentration of effort near the origin makes the difference. And after a whole lot of analysis, what we end up with is something where the beta, which was equal to half here, is improved to being a beta of 1 without increasing the overall cost. And so then we get an epsilon to minus 2 log epsilon squared complexity, even coping with this nasty case with the discontinuity. It was a nasty piece of numerical analysis. That was very satisfying to get to the end of that. I didn't say anything about this curved bit, which is where we're sort of joining up between having lots of samples close to zero and not so many samples far away from zero. In this curved region, we have enough samples to be sure with very high probability that we have correctly identified which side of zero the expected value is on. It actually decays like delta to the minus r. We need, let me see if I remember correctly, we need r to be greater than 1 so that the cost associated with this curved piece doesn't get excessive. We need r to be less than 2 in order to be sure that we've got enough samples to know whether or not we're on the right side of zero. Yeah, so there are reasons for all of this. Oh yes, it says that here. Right. I'm just looking at the time. Yeah, there are some other challenges to do with the fact that in financial portfolios, there are a very large number of different products being added together. And so that's potentially a huge cost if every single time you have to evaluate every single financial product. But actually, there's another game that you can play here, which is that the portfolio is a sum over products of the value of each individual financial product. I'm going to multiply and divide by a probability pizza by. So that's equal to that clearly. And then that is equal to the expected value of P, index capital I divided by little p index capital I, where capital I is a random index which takes value little I with probability p sub little I. And so that is equal to that. And so rather than sampling all of the different financial products, you just randomly sample one, or you could take an average of randomly sampling half a dozen or whatever. And so what that does is to greatly reduce the computational cost again. And so the cost no longer depends on how many financial products we have in the portfolio. Okay, right. With the medical one, it's very much the same thing, that we have a fine average based on 2 to the L inner samples, and we have 2 coarse averages based on 2 separate halves of that 2 to the L samples. And the analysis, we end up with a beta of 3 halves, and so that gives us our epsilon to the -2 complexity. Okay, so really, I think we've got a good handle on what to do now with nested expectations. Takashi Goda's also got new papers on expected value of sample information, expected value of information gain. So that's yet another thing. Yeah, so Al Haji Ali has a paper on doing the nested multi-level. Oh yes, sorry. This is nested multi-level because what I described before assumed that each sample could be obtained with order 1 cost. If in fact in a finance setting we are wanting to solve an SDE, then it isn't an order 1 cost. We also have to think of the discretization error and the time stepping cost. And so what he did here was to bring in the ideas from Rhee and Glynn for unbiased estimation from an SDE. And so that's come in the nested sense. And then there are other people, Lucas Spruck and others, looking at similar kinds of issues with McKean and Vlasov equations. So there's still lots of work to do. Okay, so this brings me to the various papers. Yes, so those are the original papers. These are the ones that I've done with Al on the risk estimation. Paper with Takashi on the expected value of partial perfect information. A more recent one on expected value of sample information. And yeah, his expected information gains. Okay, so I think that's the final slide. So again, be very happy to try and answer any questions that you may have.